And again, the subject is learning in dynamical systems and control of dynamical systems. So the subject is learning and control of dynamical systems. Which I will add another component today, which is called reinforcement learning. Which captures one aspect of this, namely the control aspect, or decision making. I believe exercise 3 is due today, right? Good. I haven't had time to write a new exercise, but I will, and that will be posted on Tuesday, next Tuesday. Next Tuesday I'll be teaching as usual, here. Next Thursday, I won't be teaching, so we'll have maybe a review session. PAs will be here, or in some other location if you prefer. I would say here, and do some kind of review over the material if you have time for questions, answers, and so on. A few people told me that they find some of the material or some of the questions challenging, and my answer is that's a good thing. So you should be happy about that. It means you're learning something you didn't know. That's why it's challenging to you. So my goal in this course is not to kind of give you a list of topics and read through material, but rather to dive in deep and engage you and give you challenging exercises. This way you solve them, and if they're hard for you, I hope they're hard for you. If they're not hard for you, you're more advanced than me. You know, you should be taking something else. If they're a little bit hard, that's a good thing. You should be happy about that, right? That's a good sign, and I hope you will continue. And as I said in the very first lecture, the goal of this is a grad level class. The goal here is to teach you tools that will help you later on in your career, whatever it is. So critical thinking, how to do rigorous theory, how to prove things, how to think about problems in a rigorous theoretical way, and I hope you can take this knowledge with you. And it's not going to happen if you don't challenge yourself a little bit. That's a good thing. Don't worry about the grade, don't worry about anything external, which is really not important. What is important is your own brain, how it develops and becomes smarter by learning what you learn. So next Thursday, again, not here, I'll have Gon and Anand and Rohit, who are your TAs. They will be here, and they will be able to answer questions. They might prepare something, I'm not sure. If you want to, you can prepare some review if you want to. So I'll discuss with them what's the best way to do it, and if you have any suggestions, please reach out to us, and we'll have some kind of review over the material, especially part 1 of the course, and not part 2, which I started on Tuesday. So let's continue with part 2, learning and control of dynamical systems. And the component I'll add today is reinforcement learning. If you remember, the setting is different from the one that we have studied in the part 1 of the course. And the reason is that we have an underlying generator of the signal. So we denoted that by a state xt plus 1, which evolves as a dynamics function from the previous state, a control signal, and a noise. So this was the formulation that we use. F is a dynamical system, dynamics. X is the state. U is the input or control. It is usually called input if our goal is to learn. Oh, here's the physics student. I'm glad you're, Anthony, right? Yes. I'm glad you're joining because we had some physics examples on Tuesday. We missed you. So U is the input or the control, and then W is the noise or perturbation. And we gave a few examples of dynamical systems that come from physics, such as a double integrator or a car that moves by force. Vertical ventilator, I think I gave you, and then the other example I gave you is of a dynamical system is a neural network that produces tokens, such as an LLM or the brain. Then we distinguished between two different goals. Oh, in addition to that, so this is the dynamical system, it's fully observed. Here, for example, there is a state that we can assume we can see. This was the case when we have maybe a car, but it's not the case when we have an LLM. So we also had an observation, yt equals g of xt. This g is the observation function, and this y is the observation. And then we distinguished between various sub-cases here. We could have an observed signal that's very low dimensional compared to the state. That is the case, for example, in an LLM. We see the token, or we see the word that we're speaking or hearing, but we don't have insight into the entire neural network state, weights, and connections, and so on. Then we can have two different goals, or two general different goals, but there could be many others. And we distinguish between learning. Learning means we're trying to predict yt by yt hat, and then we suffer a cost, which is yt hat minus yt, let's say squared or some other loss function. So here, this is a prediction problem. It's very similar to the first part of the course, where, for example, when we talked about online learning. But there was a difference. The difference is that the signal y, the real signal y, comes from a generative model, comes from a dynamical system. And the other problem that you can consider is control or decision making. And here the problem was to choose u1 up to ut to minimize some cost, either average cost over the entire trajectory, or worst case noise over the perturbations, and we distinguished between optimal and robust control. So all this we defined on Tuesday. Any questions or anything I'm forgetting and you want to remind? Okay. So after defining the setting, which I'm now going over more briefly than I did on Tuesday. Yeah, Elijah?
Sorry, I had a question about the cost function in the control setting.
Mm-hmm.
So you have written that the cost is a function of the observation and also of the input. But my understanding is that the observation is a function of the state, which is a function of the input.
Right.
So I'm wondering why u is being explicitly called out in the cost function. If there's like an important reason why it's a function of both.
Well, the observation is a function of the control, that is correct, but it's a function of the previous control. So the way, I didn't write the precise protocol here, but the protocol is you're seeing a observation y, and then you're producing control u. And then you see another observation y, and then you produce another control u, and so forth. So that's the instantaneous control you're putting in. And if it was a function of, for example, the future observation, then I didn't need y. But that's also not reasonable that I can see the future observation. Yeah. Because I need to make a decision right now. So the example I gave that illustrates the cost was, for example, when we have a car that we're trying to push, use the force. And in that case, this was a quadratic cost that incorporated u squared. Plus, if you remember, that was observation where the state was the same. At that point, it was the fully observed system. Was the distance of the state to some other state. So we want to push the car somewhere with minimal force over time, which is energy or power or work or whatever the physical quantity is. Okay, so yeah, this was one example. And then there are many different variants, and it's kind of hard to talk only about one and not the others and so on. So I'm keeping it general at this point. We have variants that full observation. Full observation means we know the state X. If we know the state X, this system is Markovian, meaning the next state depends only on the path, on the previous one, and not on the ones before it, by this equation. So in some sense, you don't need memory at all. If you know the state, you don't need memory more than the current state. Okay? That is the case for basically any physical system. If I know the state to sufficient precision, I don't need to know history at all. I have, let's say, this chalk that I'm trying to balance on my hand. If I know the position, I know the momentum, I know the angular velocity, I know all of these things. Who cares how I got here? If I got here from here or from here, that doesn't matter for the evolution of the state moving forward. That's a physical fact about reality. Okay? That's called Markovian. If, on the other hand, I have only partial observations, where's Lian? Okay. I remember because I asked her this question. So if I have only partial observation, then it's not necessarily Markovian, and I might only see partial information about the system. I might need to see more memory in order to fully reconstruct the state or know where I am or understand what's going to happen in the future iterations. Okay. So, yeah, full information versus partial information. It could, this dynamics and observation function could be linear or nonlinear. The noise could be adversarial or stochastic or zero. And there are all these different settings, and all of them are interesting for different problems. I'm not going to enumerate all these cases because there is no point, I think. Every time we have an example, we'll describe what happens for that example and which of the scenarios is actually happening. Okay? Good. Then we talked about basic questions. What can we even do? So I'd like to solve the most difficult problem here, which is control of a nonlinear, unknown, partially observed system. Unknown means do I know F and G? And sorry, known means I know F and G, I know exactly what they are. Unknown means I don't know what they are. That's another distinguishing factor. So of course, I'd like to solve the most difficult case of them all, but for that, we need to reason about, that's what I like to do in this course, reason about from basic principles. What can you even hope to do? And we talked about the basic properties of dynamical systems. For example, maybe the most basic one was stabilizability. F. And then we'll define it. We said F is stable, stabilizable, if and only if for every starting state x0, there exists a sequence of controls such that xt goes to 0, xt going to infinity. So I can drive the state to 0 from any starting state. Example would be, oh, here is Leon. Hi. So for every starting state, we can drive the dynamics or the system to 0. Good. And then we said, okay, it seems like it would be nice if given a dynamics function, we can identify whether it's stabilizable or not. This seems to be an easier problem than controllability, which I defined controllability too. It means I'm not going to write it again. I can drive the system from any starting state to any other state I want. That means I can control it. This is easier. Of course, it's easier than minimizing a sequence of convex cost functions, which is, this is a special case, right? The convex cost functions are norm squared of the state, maybe. So this seems to be a very basic thing to do. So the question is, can I decide, given F, can I decide if it's stabilizable or not? So let's start from there. Easy question. And the answer that I gave but we didn't prove end of last lecture, so let me do it now. The theorem says the following. Deciding if F is stabilizable is NP hard prove this fact. And to prove that, I'm going to describe a family of dynamical systems that deciding whether they are stable or not is NP-hard. And I'm going to do it by reduction from the problem of 3 sum. Okay? So if I show you that, it means you have a method of determining stabilizability you can use to solve 3 sum. That is a very unlikely machine that you have invented there. So let's find the formula, a 3-sat formula. Such as this. So a 3-sat formula, if you remember, this is a conjunction of terms. Yeah, Colin?
For the theorem, is it like for, I don't know the way it's written, like it implies any, determining if any system is stabilizable. Is it only, like can we determine it if it's like polynomial 5?
Oh, okay. Well, by that I mean, so this is, you're right, it's written.
You said even if it's.
Right, so suppose that f, the kind of more formal way to write it, suppose that f is a polynomial of degree 6. Well, here's the most general way to write it. Given a dynamics function f, it is NP-hard to decide if it's stabilizable, in generality.
Oh, okay.
Now, if it's dynamics, it could be polynomial of degree 1, 2, 5 million, or not even polynomial. I'm including that in my family of dynamics. A more stronger theorem says, look, even if I guarantee you that f is a polynomial of degree 6, even then it's NP-hard. So this is a stronger theorem because it applies to a more narrow set of dynamics, which is supposedly easier, right? So I'm guaranteeing you it's polynomial of degree 6. Even then it's going to be hard for you to determine stabilizability.
What's the choice of 6 specifically?
It's what I can prove. If I could prove for 2, I would prove it for 2. But I don't know how to prove it for 2. And for 1 it is false. So dynamics of degree 1, I can determine stabilizability. Why? How do you determine if a polynomial of degree 1 is stabilizable or not?
Oh, it's coefficient.
It's what? Kia?
If it's degree 1, I guess it's just
Well, degree 1 could be a linear, but can be high dimensional. Can be high dimensional system. I guess it's not as trivial as I was saying. Yeah, Joshua?
If you have a degree 1 system, then like the composition is linear as well, and so it just matters if the slope is like non-zero or something.
Correct. What is the slope? I don't necessarily mean input degree 1. The input degree can be high. So
Or sorry, wait.
the input degree can be higher than 1. The degree of the state. The state doesn't have to be a scalar. It can be a vector in high dimensions, right?
Okay.
So what does it mean? But you're on the right track.
If the determinant of the Jacobian is like non-zero or something.
Yeah, something like that. So there is some eigenvalue condition which we'll get into more rigorously later on, maybe next week, which will determine it. So for example, if I have a system which is not controllable, just a system. Linear system means that xt plus 1 is axt. This is a linear dynamical system without control. Maybe there is noise here, maybe not. What determines if this thing blows up or not? Yeah, Joshua?
Its operator norm needs to be less than 1.
Exactly right. So if the operator norm is less than 1, strictly less than 1, the xt is going to drive to 0. And otherwise, it's not going to drive to 0. If it's bigger than 1, it's going to drive to infinity. And if it's exactly 1, it's going to hover somewhere in some constant. Make sense? So, Colin, back to your question, how did I get to that? So, if the degree, it makes sense that when you have polynomial of lower and lower degree, the dynamics are less complicated. Makes intuitive sense. You can prove that, right? So you have polynomial of degree higher and higher degree, you get a more expressive family of dynamics. Degree 1, you can do it. And many things of degree 1 we can do somehow. So, but polynomials of higher degree, I'm claiming is hard. Even if the degree is not that high, just 6. So this is, in that sense, it's a strong theorem. Does it make sense?
Does proving 6 then imply like anything higher than 6?
Yeah.
Also follows.
Yeah, because if you have a polynomial, if I guarantee you that the dynamic is of degree 7, great. I can make the coefficient of the 7th degree 0. Special case of degree 7 is the degree 6. So, yeah. Yep.
So, does this theorem also mean like if you had any function, right, and then you took some kind of like high dimensional Taylor approximation of it that returned a polynomial of degree less than 6, would that be stabilizable? Or would that be even useful if you were to approximate a function with a polynomial and see if it's stabilizable?
That's a good question. So you're asking if I approximate a given dynamics by a polynomial, can I get insight into what the dynamics is doing? Is it stabilizable or not stabilizable and so on? Well, it depends how good your approximation is. So if it's a great approximation, if it's exact, then yeah, you can determine something about the polynomial. That's good. Otherwise, you have an approximation error that you need to say something about. So it depends on how well the approximation is, how good the approximation is.
So if you were to like restrict the system within like a small neighborhood around the point you're approximating around, and then like use a polynomial to approximate your function, would that be, is that like a practical thing to do?
Yeah, it's a very useful, this paradigm of local approximation in general is very useful. It's useful for dynamical systems as well. Usually what people will do, they will approximate a polynomial of degree 1 by taking the Jacobian. That's very useful. That's called LQR in some sense, or ILQR. There are various methods in control that do that, which I hope we'll get to. Yeah. Yeah.
So are we able to prove that for polynomial of degree 5 is not?
No, actually the theorem is true even for degree 3 or 4. It will be in your homework to improve the degree.
I think it's 4.
4.
Because 2 times 2 is 4. Because this is 2 times 3 equals 6, right?
But I think Amirali proved it for 3, maybe. So there are some improvements. 2, I don't know. I think, my guess is it's not hard for 2, but I need to check. Yeah.
The linear dynamical system you gave us an example doesn't have an input or a control. I'm wondering.
That's right. So when you have, we'll talk about it more, but a linear system with a control will have plus b ut. So ut is the control. Then you can ask, is this system stabilizable or not? It's a very interesting question with a very interesting answer. So the Riccati equation comes out of it. A lot of interesting math comes out of this. This is the paradigm of Kalman filtering is this. So very interesting stuff. We'll talk about it. But already, you have already asked me things that are open. So for example, is a polynomial of degree 2, can you determine stabilizability of a dynamical system which is a polynomial of degree 2? I don't know. You can ask ChatGPT, it will tell you. My guess is it's not known. And you can probably, if you're interested, you can research it. If you're mathematically inclined and you want to research this area, you can. There are a lot of interesting open questions here. Yeah?
Wait, sorry, do you mean polynomial degree 6 in x or u? Because x is a function.
In both, yeah.
Oh.
In both. So usually, yeah, that's a good question. So both. But I'm going to prove it even for only in U. That's what I'm going to prove it for. And it's going to be degree 1 in X and degree 6 in U. So even stronger than what I'm saying. Any other questions? So this is interesting. These are lower bounds. Already you've asked me some questions that are interesting. Much more interesting stuff is coming. Okay, this is more state of the art in my opinion. But this is an old kind of topic of study. So let me define the dynamical system that will correspond to an input formula. Here's the input formula. And now I can define P of phi. So, sorry, F of phi. So I'm going to have x t plus 1. It's going to be F of phi x u. I'm going to define this kind of dynamics. So how am I going to define it? I'm going to do the following. So for every clause here, define a polynomial by doing the following. So let's take this clause, for example. So the polynomial corresponding to clause 1, which I denote by P1. So P1 of u is going to be 1 minus u, 1 times u2 times 1 minus u3. So the way I chose it, u2, 1 minus, and so on, is by looking at the clause and looking whether the literal here was the actual literal or its negation. And according to that, I determine the sign 1 minus or not 1 minus. So if I have, for example, P of a clause, let the clause be, for example, not xi or not xj or xk. So this is going to be ui times uj times 1 minus xk, y minus uk. So I will have a variable for every variable in the SAT formula, and then I take either the variable itself or 1 minus it, and take the product of them, and that's how I can create a polynomial of degree 3 for every clause. Is this clear? Yeah? Now I can define, so this I define for every, given a SAT formula over variables, so the variables here are x1 up to xn maybe. Then I defined a polynomial for every clause. So the variables now are going to be u1 up to un. And my polynomial, so f of phi, hat, the first polynomial I'm going to find is going to be the following. So I'm going to sum up over all clauses, take the P clause of u squared, and to that I'm going to add summation over all variables I from 1 to n ui squared 1 minus ui squared. Yeah.
Okay, so UI is a vector, right? So when you do 1 minus UI, what exactly are you doing?
No, ui is not a vector. So
Okay.
so given this formula is defined over Boolean variables. I'm now defining variables. So each of them is a real value. Each of them. Altogether, it's r to the n. Each of them is a scalar.
Oh, those are the components of U. Okay.
Yeah, exactly. So u sub I is the ith component of u, the ith coordinate of u.
Thank you.
Sure. Any other questions? Yeah, Ben?
Does 0 correspond to true or false?
Good question. I think 1 corresponds to true and 0 to false. But it doesn't really matter. So this is satisfied. So x, if this is 1, I guess 1 is true. So 1 or something, this is going to be, I want this to be 1, or this clause. And the whole thing to be 1.
So then in the polynomial, if you plug in 1, then the whole, and like the multiplication gets zeroed out and you get false.
You're right. So the other way around. so 1 is false and 0 is true.
And then I think you get the same problem.
No, one of them is going to be true, the other. So let's see. So if I have, here is what I want to say. I want to say if there is, so this is my polynomial. Now my claim is satisfying assignment to phi, then exists a zero of p f phi. This polynomial f of phi has a zero. That's my claim. There is a point in the Euclidean space R to the n where it has a value of zero. So let's see that. Suppose there is an assignment that makes all of this true. So this means, wait a minute, this might be so I want at least one variable here to be true. That's what I want. If there's an assignment that assigns to be true, I want one variable here to be true. So this means, so let's take 0, 1 to be the assignment. And now what will happen here? One of them has to be true. So this means the whole, I believe this is 0. This whole thing has to be 0. So this is 0 because one of them, so either this is 0, so one of them has, at least one of them is 1. If one of them is 1, this product has to be 0. Yeah? Ben.
So one is true.
Sorry?
So
One is true. One is true. Yeah, 1 is true. 0 is false. So if this evaluates to 1, it means at least one of them evaluates to 1, which means that either this is 0 or this is 0 or this is 0. That's what it means. Yeah?
Yeah.
Good.
So you're saying if the polynomial will evaluate to true if it's 0?
It will evaluate to 0. The polynomial doesn't evaluate to true. It evaluates to 0, to real number. Polynomial is a real number. Now, if there is an assignment that makes this formula to be true, it means in every clause there is one variable that is 1, and therefore in every clause this thing is going to be 0. And therefore the whole polynomial is going to be 0. This is going to be 0 everywhere. The sum over everything is 0.
So truth is 0.
True is 1. True is 1. True is 1, so let's say x3 is 1.
Well,
Okay?
I'm saying like the whole truth value of that statement is it not supposed to be encapsulated in the polynomial?
It is.
No, it's not. It's the polynomial is defined such that if the three-step problem evaluates to true,
Yeah.
then each polynomial corresponds to one clause, and so if the SAT problem evaluates to true, then each clause evaluates to true,
Yes.
which means each polynomial evaluates to 0.
Both of what you said is true. What you said is true. What you said is also true, I think. What did you asked me if there is, so what I'm claiming the following. If there is a satisfying assignment, then I can assign the variables here to be 0, 1, according to true, false. And this means when I assign them here to 0, 1, all of these all of those are going to be 0. Because in every small polynomial, there's going to be one variable that's set to 1. And that means that the product here is going to be 0. So when I sum up all of them, this is going to be 0 also. And they're all 0, 1, so this is also going to be 0. So the whole polynomial is going to be 0. Okay, so that's my claim. If there is a Exactly correct, yeah, exactly correct. Maybe, are you okay, Ben, with this part?
Yeah. The only thing that was confusing me is that like in like the x size, one is supposed to be true, but like the polynomial evaluates just zero.
Yeah, it kind of flips the one and the zero. But it might be easy to see if I had them all without the note, you know, x1, x2, 3, and it's going to be 1 minus 1 minus 1 minus, okay? Yeah. So, yeah, everyone okay? Everyone with me? So if there is a satisfying assignment, I can make the polynomial to be 0. On the other hand, if P5, or why do I keep calling it P, F5 of U equals 0, so there exists an assignment for some U, then I claim that phi is satisfiable. Okay, why? Why do I claim that? Well, if it's 0, then I can, first of all, I know that every UI is either 0 or 1. It cannot be anything else, otherwise this thing would have valued to something else. And then I can actually define the assignment to be xi to be true if it's 1 and false if it's 0. And you can see that for every clause, it must be 0. So one of the variables must be set to the correct literal, if it's not or not. Or true. Okay. So I can define xi to be false or true according to UI being 0 or 1. And we know that UI are binary. And all clauses are satisfied. So you know so P of clause of U basically equals to the clause xi or xj or xk, with the notes here as needed. So that's why it's satisfied if and only if you follow the 0. Equals 0 if and only if this thing is satisfied. Okay, I didn't write the whole proof, but you can see now, I hope. Anyone needs more details for that? Yep.
I have a really dumb question. Why is this degree 6?
Good. Let's see. So what's the degree here?
Oh,
4.
I see.
This is degree 4. But we also have P clause squared. Each P clause is a polynomial of degree 3. So overall it's 6. Yes. So yeah, degree of n times 5 is equal to 6 by construction. Yeah.
So is this, I'm confused because like the control doesn't have to be binary, right? So like,
For sure. Yeah.
yeah, so how does this?
I'm not done. I'm not done with the proof. I'm not done. Yeah. Part 1. Yeah.
So I guess if we deduce it from a different problem, then we can reduce the first part. Like
Yeah.
if we like have less,
Yeah. What will you reduce? That's a good point. What will you reduce it from? Very good point.
like something that has two things in one.
Okay. Give me an example.
I guess two STP doesn't work, so like max two XTP. Like
Okay, very good. Very good. So I believe that's in homework. Yeah.
Let's exercise one in this chapter.
Yeah. So very good. So then you'll get degree 4 in this case. Very good. So actually the theory can be strengthened. I believe Professor Ahmadi from Murphy has a improvement where he gets degree 3. And I don't know if it's tight or not. My guess is that it's tight. But degree 2, you can actually, Devin might start that pretty good. That's my guess. But you're all welcome to check on ChatGPT. Questions? Oh, I'm not done. every starting state I can drive to zero with some sequence of controls. And indeed, if there is, so if there is a satisfying assignment, then there is a u that will make the polynomial zero, so this is going to be zero. And then xt is going to be 1 minus epsilon to the power number of iterations is going to zero. So if is satisfiable, then xt can behave like 1 minus epsilon to the t, that goes to zero, xt goes to infinity. And otherwise, if phi of u is bigger than some epsilon, for some epsilon, so this is the number from which is bigger than, and then xt does not, so it reaches something maybe infinity, or not infinity. So if you could determine that the dynamical system is stabilizable, you could determine whether a given input formula is satisfiable, and that's NP1. Any questions? Yep.
How do we know that if it's not zero, then it's bounded away from zero? Like, can't I, like, say, push to infinity or push to zero such that it approaches zero?
Well, I can define, I didn't say what epsilon means here. I can set it to be exactly the minimum value of the polynomial. So if it's not zero, it's bounded away from zero. There is some value, I'm not making this 100% rigorous, but you can make it rigorous if you want. There is some value in which the polynomial is bounded from below. It's not zero. I guess you would have a situation where it's infinite close or something, but you can kind of show by more inspection that there is a value that's strictly bigger than zero, that the polynomial is bounded from below from. And that value can take epsilon to this.
I guess we need the set to be, like, compact or something. If it's just a real line, then it can still approach.
You can't still approach, but notice that this is a good point. This is it's an even degree polynomial, which means it goes to infinity both ends, right? And it's also non-negative. So this is actually never negative. You could always add. Okay? So actually the limit is not infinity.
Yeah, that's what I was going to say. You don't need to compact this because polynomials move to infinity at either.
That's right. So they go to infinity at either end. So therefore, if you take this on finite integral, on that finite integral, it has bound to zero. That's the math too, so not those dimensions. Yeah. Good. So to make it like 100% rigorous, there's a few more lines to write here, but I hope you will believe me. Well, you have a question?
Yes, I guess I missed, why do we define xi up there? Like, struggle to see how
Why do we define?
the xi,
Okay, so there are two directions. I mean, I want to say that this polynomial has an assignment of zero if and only if the original formula is satisfiable. So if it's satisfiable, here's the. And I want to say, look, if I found something that makes it zero, it's also satisfiable, if and only if.
okay, so it's the xi in the free set, not the x.
Yeah, not this X.
Okay.
Maybe I should have put different variables, yeah. But you can see this X is actually a scalar. This thing is a scalar, and this U is a vector. But it's linear, the dynamics is linear in X, which is a scalar, one-dimensional, and it's polynomial to B6 in the U variables. Yeah, Colin?
So does this look specifically at like states that are like xi can only be true or false? The control can only be 1 or 0. Is this like a specific type of dynamics?
It's very special, yeah. This is a very special and very, I would say, useless dynamical system.
How does it show though that like all dynamics functions of
Yeah.
polynomial degree 6?
This is a very good question. And it's a conceptual question, so we're still philosophy mode here. We're just starting the second part of the course. What does it show that all dynamics are how to stabilize? Well, first of all, it doesn't. So there are dynamics that are easy to stabilize, cannot in polynomial time decide whether this formula is satisfiable or not. But again, the degree is to go to infinity and so forth. So there are a lot of quantifiers here that I'm not saying because it will take me forever. You know, I'll spend the whole class just to write everything very precisely again. Nevertheless, that's what I mean. I mean that as a general problem, you give me some problems are easy in general. Here's a linear program. It can go to infinity. I don't care. Any problem you give me, I can solve it efficiently. And I showed that. I gave an algorithm in this class to do it. Right?
I guess one more point too is like, for the sake of like precision in the proof, should we show that like such a dynamical system, like actually write out like a dynamical system that follows these rules, like the states only go 1 or 0, and like
No,
you know,
no,
we
no.
already like
No.
we don't have to
No,
write
no,
that.
no. So the proof only works for that case. That is true.
Sure.
But the reason I'm showing you this proof, my point is not to convince you that 0, 1 diagonals of this form are hard. That would be like completely useless. I'm trying to show you how I think. And the way to think, we need to design an algorithm for the problem, or for machine learning algorithm. You want to say, look, my algorithm works in a general case. Otherwise, what's the point of it? It only works for one particular case. It's useless algorithm. So I would say, look, here's an algorithm for prediction from expert advice. Any experts, any doesn't matter how many, I have a written down, root D log n. Okay? It's efficient, always runs the time n, always does this, always does that. I don't care, the noise can be adversarial, right? That's what I'm shooting for. That was a beautiful thing this algorithm called to. Now, if now I'm thinking of a more harder problem. I want to learn an LLM. I want to learn to control a dynamical system. So, okay, of course, I don't want to do a lower bound. That's not what the course is about. I want to design algorithms. But if I want to have an algorithm that can control any dynamical system, then no, that cannot be done. I need to understand at the beginning. It cannot be done. I need to change my language now because, look, this cannot be done. These dynamics are hard. So that's why I gave you this slowdown. Someone tells me they can control the dynamical system, you tell them, no, it's impossible. How can you control these things? They need to have a disclaimer in there. Oh, they come from a distribution, they come from this, they come from that. That's the way when you become more senior, some junior researcher tells you something, you can immediately say, wait a minute, how can you handle this particular case? That's not, doesn't make any sense to me that you can handle any dynamics. No, even polynomials are hard. Okay? So, it's a back and forth. I go back and forth between the lower bound and the upper bound to kind of nail what is the right method. My motivation is method, it's not a lower bound. But I have to understand what is even possible. Make sense?
Yeah.
All right. That was a very good discussion. Thank you, Gordon. More questions? Okay. So, what's my conclusion? My conclusion is that any form of anything to do with dynamics, almost, is hard. Maybe I can restrict myself to linear. We're going to go there. Linear is interesting. We can extend it by what you said, kind of local linear and Jacobians and so on, the methods of this form, sure. We can go that route. People went that route. But for many reasons, this NP-hardness is why this kind of literature was stuck for so many years. It's just impossible to do something generic in space. It's a hard space. So what can we do? We can do two things. A, we can restrict F. So it has to be less than a polynomial of degree 6, and even less than degree 4, because of what I said. Okay, we can go that route. We will go that route. We'll see what can be said about it. It doesn't mean necessarily that's a bad thing, because there are techniques that we'll see state of the art, beautiful stuff, recently developed. Like students such as, I told you, former undergrad and other people, that basically take any nonlinear system, they convert it to a linear. Then in the linear we can do something, because it's already a linear polynomial, it's fine, we can do something there. So that's one route we can go. I would say that's the most sophisticated, more nicer route. Or we can forget the structure and linearize. So that's the other option. that and teach you everything there is to know about it. So how can I discretize dynamics in a way that makes it easy? Remember that my dynamics equation of x plus 1 was f of xt, maybe w, doesn't matter for now. And this f could be nonlinear and could be a problematic function, could be a polynomial of degree bigger than 6 or 6. So what I will do is I will treat every possible state in the world as a separate entity and forget all structure in states. So I can move to a distribution of those states. Discrete. And talk about them when the structure is linear. And now when I do that with linear transition. So this is called a Markov chain. More generally, we'll talk about Markov decision processes. Same idea, where I discretize not only the states, I discretize also the action states. So what I'm going to do, I'm going to take my states, and you can think of, for example, the car, the faults, and all that, and discretize the faults. Faults from point 1, point 2, point 3, point 4, they're all totally different. They're not one is bigger than the other. I'm forgetting that. Every possible state in the world is different. I'm forgetting that the pendulum now moves from here to here. These are totally different. Here, this one, this one, this one, and this one, all treated equally well. Okay? That's the idea. It's particularly useful for situations where your state space really is discrete. And that's interesting for many kind of computer science applications. You have an account game, you have, here is an example. So example that is classical in the AI literature. This is classical in the book by Dr. Golding. It's called Babel's World. Babel's World is an example of a Markov decision process where we have, it's like a game, so we have this grid, 3 by 4 grid. This is with a tree here, so you cannot go here. You get +1 if you reach here, you get -1 if you reach here, and you have a robot that starts here. And the robot can walk, and the robot wants to reach this kind of end state here. So I'm now talking kind of very informally, okay, I'll define all this formally, but this is a computer game. I mean, now we have much more sophisticated computer games, but same idea. So you have states of the world. What are the states? The states are where the robot is, and what are the actions? The actions can go, or actions can go up, down, left, right. If the robot is here and it goes right, it gets stuck, nothing happens. If it goes here and goes right, it goes to the minus, but the game ends when it reaches plus or minus. You get the reward of plus, +1, minus, minus 1. You want to reach here, that's kind of the goal. So what should you do? It's kind of obvious, of course, go here, yeah, or here. But then there is an additional complication usually. You say, wait a minute, so the controls are inaccurate, maybe I move up, there is some probability I actually move to the side. Now it's a bit less trivial because if you're here, and you kind of like move up, you might reach the minus by mistake. So maybe you actually want to go towards the 3, and then there's a chance you'll be here, and then you move to the +1. So you kind of have all these different, a bit more sophistication. bubbles world, I'm not going to defend myself. But any questions about the bubbles world? You've seen this before? You've seen it before? Okay, yeah, maybe an example in 324, which probably actually is 324. Okay, so let's define, how much time do I have? About 10 minutes? how do I represent states in this form? Well, I can maybe discretize all of two-dimensional space, and for each epsilon position, I'll have a state. And then what does the transition matrix look like? You could basically write it down. So from every state, where does it move to the next iteration? It's a deterministic function. There is no probability. It's going to look like 0, 0, 0, 0, 1 in some place, and 0 everywhere else. So where it's going to move to, that depends on the current position, and the speed is going to move to some other position, depending on the force. You can do this for a ventilator or for anything you want. You can do it for any dynamical system in the world. You can always do that. Just write down in fine discretization what all the states are, and each state gets a node like this, and then move to some other places depending on the dynamics. For deterministic dynamics, this matrix is going to have a special structure because it's going to be only 0, 1. That's it. There's not going to be nothing else. Unless there is noise. If there is noise, maybe you get some other numbers in there, depending on how the node is structured. Make sense? Yeah? Yeah.
You said that you can model any dynamical system like this, but it's a little unclear to me how the input, the control.
Yeah, I don't have, this is dynamic system. Dynamic system without input, without control. So if you want to add control, you can do that too. I mean, without the policy that determines control. So you'll have basically, you can say my state, so my state will include a u in it or something like that. The u is the input. And that will correspond to moving from x and u to another x, another u. Very fixed policy. But I am distinguishing, and I guess I did it in the last lecture as well. I'm distinguishing between the decision problem, which I call control or reinforcement learning, and the learning problem. So what I do is next local prediction. In some sense, the learning problem, to me, is even more interesting these days because that's what we do for next local prediction to train data language for. I do see there's a ton of structure, very interesting stuff. We can do less with control as a hardware problem, but for now, this is kind of the learning analog of not the decision analog. So I'm going to incorporate decision, that's called the Markov decision problem. But if I don't have decisions, I just have states that evolve, like the car with a fixed power, or ventilator, or any control problem with a fixed policy, that's a dynamical system. Make sense? Yeah? No? Question?
No.
Any other questions? Yeah, Kara?
Can you give some sort of like continuity or smoothness assumption on the dynamics for this perspective?
Very good. This is a really good question. The answer is yes in general. Otherwise, it's going to be not going to be very precise. So to capture epsilon precision of the dynamics, I will need epsilon to be a function of the Lipschitz constant of the dynamics. I'm kind of ignoring it now. It doesn't have to be smooth. It has to be continuous. Lipschitz continuity enough. I'm kind of glossing over it, and we'll get into more details with quantitative statements. But qualitatively, I can always do it for any interesting. And let's have some discontinuity. Let's see. So the only other things I want to say, because I'm running out of time, are that the main thing we're doing with RL or with this formulation of Markov chain is incorporating stochasticity in a much better way. So I won't say better, but structure, I got it to be linear instead of whatever I told you before. And now you can define stationary distribution. Sometimes we want by pi, so pi is pi t. And there's a very interesting theory talking about when do we have stationary solutions, how quickly, let's say I start from state one, how quickly you start running, how quickly we convert to stationary solution. Stationary solution is steady state or something. So it means after you do a lot of iterations of moving along this graph, so 0.5 you move there, 0.4 you move there, so you do million kind of iterations. But here you can see where you're going to end up eventually.
Snow.
Snow. Yeah, the snow. That doesn't matter. So at some point that's the whole stationary solution here. It's kind of a terminal state. But I could have made it more interesting by making this, I don't know, 0.9 and then 0.1 here. And now you can ask, okay, what's the stationary solution here? And now you'll tell me, God knows, I don't know, it's a complicated thing, right? I mean, it's not clear what to say, and it's not even clear. So this is kind of the fundamental question. Of ergodic theory. And there are probably lots of courses on that in math. So they're asking the following: when does there exist an unique stationary solution? It's not always the case that you have a stationary for example, who can give me an example of Markov chain? Do you have a question?
Or not?
You going to answer my question? Yeah, I didn't even complete it. Maybe you already know what I'm going to say. So who can give me an example of a Markov chain where there is no unique stationary solution? Yeah.
If you have like an irreducible one where there's two separate components, then you can have stationary solutions or any convex combination.
Very good. So let's say I have this. This is main. Then here is probability half, and here is probability half. I don't know what to call it. S and T. And this is like 1 and 1. So here there is no unique stationary solution. You can end up here, you can end up there. And the other example, the other question I had, when don't you have a stationary solution at all, for example? If we tell me that. Yeah, go on.
When we have a odd cycle.
Good. Good. Even cycle is okay too. It means it's probability 1 I move here, probability 1 I move here. There is no, on even rounds are going to be there, on odd rounds are going to be there. It's never going to be, there's no stationary thing to converge this to.
0, 1, 1, 0. Like that still has 1 half as a like a left eigenvector. Like that's still right. It's just that it wouldn't converge to it.
That's right. So, I mean, an eigenvector, a right eigenvector left, whatever the direction is, that has, this is true. So what you're saying, this is a good point. What is it? It's an eigenvector. How is an eigenvector of the matrix P? It's a left eigenvector of the matrix P. And the eigenvalue is 1. So, but this is, it does not immediately imply that this is stationary distribution. So there is a bit more, so you want for every t, so stationarity is for every t, t converges to pi. Okay, I will write